Hello, everyone. Thanks for being here. I see a lot of people in the room. I'm a bit surprised. I thought this was a very specific topic, but a lot of people are here. I hope that will be interesting to you. This is a status update about a long ongoing work to support hot-pluggable connectors with non-discoverable hardware. I'm Luca Ceresoli. I'm an embedded Linux engineer at Bootlin. We do consulting on embedded Linux and trainings as well. We have an open source focus. I mostly do Linux kernel device driver development, and I live in Bergamo in the north of Italy. So in this talk, I will first introduce the use case and goals of this work, and then describe the abstraction we are proposing in the kernel to handle that, the connector, and then give the actual status update of ongoing work for the two parts of this work, which is the connector work and device tree overlays topics, and the video output with DRM. So the use case we are working on is a product. It is a fairly standard ARM64 embedded system using device trees for hardware description, except it has something special. It has a connector in red in picture where you can connect an add-on board with additional hardware to extend the functionality. This uses a proprietary connector. On this connector, there are several lines which are not discoverable hardware: GPIOs, interrupts, PWMs, and even a MIPI CSI video output. Additionally, multiple add-on models are supported, and so there is an EEPROM on an I2C bus to detect the model ID and be able to handle that correctly, because different models need to be handled differently. For example, different panels. There is actually another use case which we are not directly working on, but it's being handled in the community, and that's about developer boards such as BeaglePlay and other, well, there are many, you certainly know about them, which are usually not hot-pluggable, but aside from that, they have very similar requirements. So they also have a non-discoverable hardware connected on the pins. And Ayush Singh is working on this, and we have discovered we have a lot of commonalities in our needs. So I'd like to ask, since I have this huge audience, to raise your hand if you have a similar use case with a connector where you have non-discoverable hardware. Whoa. I had just discovered one a few minutes before the talk, actually in the toilet while talking to someone. Yeah, it happens. But there are so many. Yeah, it's better than in a toilet. But yeah, so I'm really surprised. I'm really surprised. So don't hesitate to participate also in the community, in the discussions I will be mentioning to propose your use case. So what we are trying to do is to use device tree overlays to support this kind of use case, because the board itself is described with device trees. Device tree overlays already exist, so we are proposing to use those overlays to support this kind of use case, but those should be loadable at runtime, because in our system, the device can be, the add-on can be connected and disconnected at runtime. So we also have, for the connector, a device driver supporting the connector, which has some way to detect when a board was added and removed, and is able to read the ID of the board. So when the hot plug event happens, it loads the appropriate device tree overlay, and when it is removed, it removes the overlay. So this populates and depopulates all the devices on the system. It is a bit more complex than that because you need to read the EEPROM ID, but the principle is this. Something we need to support is to support different add-on models incompatible between each other, but using the same connector. So all compatible with the same connector. And also to support the reverse case, so the same add-on model can be connected to multiple different baseboards, each with the same type of connector. So this leads to the need to decouple the add-ons and the baseboards through the connector. Finally, there are cases where you have a main board with multiple connectors of the same type or even different types, and you can connect at any moment add-on boards to any of these connectors, and potentially the same add-on model can be connected on multiple connectors at the same time. So it looks correct, the correct idea to use the same add-on exactly to describe each add-on model, to use the same device tree overlay to describe each add-on model. So it's the same hardware, because it's the same add-on model, it has only a single overlay. So the overlay should not depend on which main board is used and which specific connector on the board is used. So that's what we are trying to model, and the model to describe that is the connector. We named that connector because it is a connector. So what is a connector? We try to generalize as much as needed to support reasonable use cases, also hopefully in the future. And so you see some kinds of connector in picture. So a power plug is a connector because it is what a connector needs. So a mechanical definition, electrical definition, pin-out definition. So this is what defines a contract between who provides some services and who uses them. The connector. So in the power plug example, which is probably a bit stupid, but it has mechanical, electrical, and pin-out definitions. Some of the connectors also have a way to discover what is connected, like USB and PCI, we all know. Some others don't, such as many developer boards don't have a way to discover the model of add-on that is being attached. However, in this case, that must be known by some other means. Typically, the user must know and manually load and overlay or prepare that in their build system. So not all of them support Hotplug, but that's just one feature that not all users will use. So the connector itself is a contract, so it needs a specification to describe what it provides and what can be used by the add-on. And this specification is, for what is relevant for the operating system, it is mainly describing pins. So in this trivial example in picture, you have a connector with pin 1 and 2 are an I2C bus, pin 3 and 4 another I2C bus. Then you have on pin 5 a GPIO, which we call GPIO 1. That's just a name to mention that pin, and GPIO 2 is on pin 7, then you have some power rails and some ground. So that's the idea. In real cases, you will have more pins, but the idea is still the same. You have a contract. And then who provides the feature? The main board need to specify how it is providing the feature on each pin. So on pin 5, you need to provide GPIO 1 by some means. So the board A on the left is providing a GPIO by one of the GPIO controllers on the SoC itself. So that will be pin 12 on GPIO controller 3. Another baseboard, model B, provides the same GPIO feature on the same pin through an external GPIO expander. It is perfectly fine, enough there is a GPIO on pin 5. On the opposite side, add-ons need to tell how they are using each pin, if they are. So in the left example, you have an add-on with some sensor, which needs a reset pin, and that is connected to GPIO 1. And as you can see, GPIO 1 is described as connector 1. So GPIO number 1 of the connector. On the right-hand side, we have a backlight on a different add-on, which has an enable GPIO needed, and so it connects that to GPIO 1, pin 5, so the same pin. So you can see that the description for them is the same, so they both reference the connector. One key aspect is they cannot reference the GPIO controller on the system on chip or the GPIO expander, because the device tree of the add-on doesn't know on which board it will be connected, so it must be generic. It cannot reference anything beyond the connector. That's one key idea. So our work is in progress to implement all of these together with my colleague Hervé, who is focusing on these parts. So the current status, we made initial proposal with the connector driver in May last year, so it's a long time ago. You have a link to the most recent patch series with all the work, the complete work. After that, we continued working, but sending separate series for various aspects, so you don't have the big picture after that. And a milestone was Linux Plumbers. Last year in September, we had a session with Hervé to discuss our initial proposal. There was a lot of discussion, very good discussion, which led to many improvements, and our approach has become mature after that. So thanks to all the community person who contributed to the discussion also in the hallway. So currently our latest proposal is based on export symbols, which is a new node to be introduced in the device tree. It is inspired to the underscore symbols, which is an internal one used in overlays, but the difference is that the internal symbols allows to touch anything in the whole tree, while export symbols only allows to reference from the overlay what is in the connector. So it doesn't allow to go beyond the connector. So this allows full decoupling between the add-on and the mainboard. And in this proposal, we are using Nexus nodes for GPIOs, interrupt, PWMs, and similar resources. So let's have a look at how it looks. So let's start from the right. On the sensor, you reference, as I showed before, the reset GPIOs points to GPIO 1 of the connector. You cannot point to GPIO 3 here. This is wrong. You cannot reference to the mainboard. And then on the left side, here is how you define the connector in the mainboard. So in the mainboard, you have the connector. It has a compatible, not shown because there was no room on the slide. It has a compatible, so a driver can be loaded. This is a Nexus node, the GPIO map. More properties are needed, but this is just a simplified form. So you are basically telling this node, add-on connector, is providing GPIO 1, and this is basically remapping GPIO 12 from the GPIO 3 of the system on chip. So you are remapping GPIOs from anywhere in your system into the connector, which is what happens in wires on the board, after all. And then there is export symbols. Export symbols is used in our proposal to allow exporting basically something that references to the connector, and then the add-on can have a p-handle reference to the connector. If you look at the different baseboard, different mainboard, but when you attach the same add-on model, on the right-hand side, it's the same. The correct line is the same. You always reference a pin on the connector. While on the left side, the same pin is provided in a different way from a GPIO expander. And also in export symbols, the connector points to potentially a node with a different name. Doesn't matter. Enough you export the needed symbol. When you have a more complex system with multiple connectors on the same baseboard, you always have a single DTBO if you are connecting two instances of the same model of add-on. And so the connector reference will resolve thanks to the node where the overlay is attached to. So the connector driver knows if you are attaching to this or to that node, and then it will handle the resolution. This work was proposed by Hervé. First proposal was last December, then a V2 was sent in April, not very much different. There was another proposal by Ayush, which I mentioned before, basically implementing the same thing, but in different repositories. The reason is our proposal from Hervé was on the kernel, bindings, and along with the implementation, while Ayush wants to have FTT overlay to apply overlays offline. And so he proposed to add the specification to the device tree spec repository. So it's however, the content is the same. The feedback was a bit slow. We had some also recently, a couple of weeks ago, I think. So Christophe, somewhere in the room, had some issues about syntax, while Rob Herring, the directory maintainer, was skeptical about some core aspects of the idea. So discussion is in progress. We actually are going to discuss these to try to understand what is the correct representation. So maybe the export symbols idea will not be applied in the end. It could change over time. Another part of the connector work is about the bus extensions. So for I2C, SPI, and similar kind of buses, the description in the registry is different. You cannot use Nexus node in the same way I've shown. In those cases, you have a node representing the bus controller or the I2C adapter, SPI controller, etc., and subnodes inside that to represent the devices connected on the bus. So we need a different description. And the proposal here is this. So of course, from the overlay, you cannot reference or add a node under SOC I2C1 because it's mainboard specific. So in the connector description, we propose to add this node, I2C control, for example, I2C sensor, whatever is the name of this I2C bus in the connector specification. And there is an I2C parent property pointing to the actual I2C controller. So in this way, you have, on the mainboard DTS, you define the connection between the I2C controller and the pins on the bus. And the other part, so from the pins on the connector to the device using it on the add-on, you just have to add a node, but instead of adding that under the actual controller, you add that into this sort of proxy node, which we call bus extension node. And this way, the I2C core is able to resolve to the actual adapter that is used in the specific configuration. So this proposal is also progressing slowly in terms of feedback, but the principle seems to be accepted. There are still discussions about the exact representation. There could be a compatible to tell this is an I2C bus extension or maybe not. So the details are still to be ironed out, but the principle seems to be okay. And so we have pointers to the discussion here. So we propose that at Plumbers again in the discussion. Recently, we have the feedback. We also had good feedback from Wolfram about the I2C implementation, but of course we need to sort out the bindings first. Finally, we don't have SPI in our use case on the connector. However, Ayush has SPI on the connector is implementing. And so he sent this series to introduce SPI bus extensions, which is basically the exact same idea as I2C, just replicated on SPI, and it works just as well. So there was not much discussion on this. Basically, what will be the outcome of the I2C discussion will also apply on SPI. I'd like to just mention a totally different approach to what I've been presenting so far. So there has been some debate about global versus local device tree overlays. So I'm talking about local only in this talk. The global approach was proposed by Andrew Davis, I think working on BeagleBoard. And the idea is to use the old symbols node, which was not accepted to be used for this purpose in the past. So he's trying to push to change this idea. However, his approach is a bit different. It requires some adapter device tree overlay between the main tree and the actual add-on tree to decouple add-on and mainboard. So there is a different technique to decouple, but it doesn't support removal. And that's the reason we are not considering for our use case where removal is absolutely required. So you have a pointer to, there's a clickable link there to the discussion started by Ayush about those two. So if you want to have more information, you have a link. So the other big part of the work is about DRM, so video output. which is what I'm focusing on mostly. So in DRM, the classic DRM pipeline is, as in the first picture, a CRTC, an encoder, a connector, and a display or a panel, optionally with one or more bridges after the encoder. And at the moment, in DRM, the only part that is hot-pluggable is the display. It is a problem for our use case, because in our use case, we actually have one video bridge after the hot-plug connector. So it's in the add-on. So basically, we have MIPI CSI going through the connector, which has fewer wires, and then there is a DSI to LVDS bridge, because the display panel is an LVDS. This is not possible with DRM currently. The reason is that bridge drivers up to recent kernels, up to 6.15, just allocate a struct DRM bridge on probe and deallocate that on remove, which was fine so far, because even though multiple parts of the DRM stack take pointers to bridges and they store them for a potentially long time, so if a bridge gets removed, the driver gets removed, the struct will be deallocated, and so there could be a use after free. You still have a pointer to a bridge that has gone deallocated. So use after free, of course, this cannot be accepted. It was not a problem up to now, because a DRM card can only be removed entirely, not partially. You cannot remove the tail of the pipeline, which is what we are working to achieve. So I sent a proposal. It was in March last year, so it's a long journey. The idea was to add a hot-plug bridge. So that's an additional bridge driver, which sits exactly where the connector is. So it represents the hot-plug connector in some sense. And it pretends to the previous components that the pipeline is complete and can be probed. Otherwise, what happens is that DRM will not populate the video card, and so user space relying on the video card will not be able to work. And also, if you remove the video card, if you remove the add-on, the video card would be forced to disappear completely, which user space might be needing. This work continue. Also, the latest big picture series is the same I mentioned for the connector. So in February last year, there was another session at Plumbers last year to discuss this, with a lot of discussion continuing for a long time in the hallway, which Maxime Ripard especially contributed, and this led to what I call the ground plan, because it's a lot of steps. So the ground plan is roughly made of 4 chapters. So first, we need to introduce dynamic lifetime for DRM bridges. So they must be able to disappear, and their lifetime must be handled dynamically. Then we need to gracefully handle atomic updates when the bridge is being removed. Chapter 3 is some issues with DSI, the communication between DSI host drivers and DSI device client drivers. And finally, well, last chapter is everything else. So it still has to be a bit sorted out. So chapter 1 is the one that is actively progressing at the moment. So the problem, as I said, is bridge drivers allocate their structure, including their DRM bridge structure, on probe and free it on remove. That cannot be accepted anymore, because other parts of the kernel will take a pointer, and that would lead to use after free when the bridge is removed. So the first step was introduce dynamic lifetime on DRM bridges. So now there is a new API to allocate a bridge, which is mandatory for bridge drivers, DRM bridge alloc, which allocates a struct DRM bridge with its containing struct, and initializes a reference count. So there is now a reference count for bridges, and that reference count is released when the driver gets removed. So if other actors in the kernel take a pointer, they also need to increment the ref count and decrement it when they are done with the pointer. That means the allocation could be kept for way long time after the driver has been removed, so that you avoid use after free. So this work, the first part of this work, the new API was merged in kernel 6.16, and then the next step was to convert all bridge drivers to use this API, so they have a ref count and they can be dynamically managed in terms of allocation. That was merged in 6.16 RC1. There might be some leftovers, I hope not, but I'll mention how to discover that. Most conversions are pretty trivial. Then I also introduced K-unit test of the new API in the same kernel version, and then I started the other part of the work, which is converting all the users. So all those parts of the kernel which take a pointer and they need to get and put a reference count. So in the same kernel version, I converted the users inside the DRM core. And then I'm in progress with converting all the other users. So basically, there are multiple accessor APIs which return you a bridge pointer, like get next, get first, get last, etc. And I'm converting them one by one. Some are merged and should be in 6.18. Some are in progress. Some depend on others, so they are still pending before I send them. But this is progressing quite smoothly at the moment. I also introduced some debugfs improvements. So because bridges are not used to not be visible in debugfs until they are added to an encoder, I also added a bridges debugfs file in the DRI directory, which shows all the bridges that have been added to the system. So you can see all of them, even though they are not yet attached to any encoder. And I also sent another series currently under review, which adds the ref count presented on the same file. And she also shows removed bridges, so bridges where you called DRM bridge remove, but are still waiting to be deallocated because there are still some reference count. The reference count has not yet dropped to 0. And so that's all for chapter 1 of the grand plan. So a small note, if you see this warning, that means you probably have a bridge driver that has not yet been converted to the new API. So again, I should have converted all of those in the mainline kernel. If you have an out-of-tree driver or something you are not yet sent to the mailing list, you might see this. You have to update to use the new API. The first line is something I added in 6.17, so if you are on 6.16, you will not see the first line, which is self-explanatory, but if you see a ref count warning on your bridge driver, then it's probably the situation. Okay, so the other chapters of the grand plan, Chapter 2 is handling gracefully atomic updates during bridge removal. So there are now at least 2 code paths that you can enter independently and concurrently. One is you are removing the bridge because someone physically removed the add-on, and you are doing an atomic mode set change or other operation. So this can be very dangerous. You are in your atomic callback, you are accessing some device resources while you are removing them. So we need to protect from this. So the proposal was to introduce DRM bridge enter and exit functions. So every function, like atomic callbacks, that needs to access device resources, needs to call these to avoid entering the critical section if the device has been removed. And then on removal, you need to change DRM bridge unplug to tell this bridge is gone. So after that, DRM bridge enter will prevent you from entering the critical section. So it's a bit tricky to explain, but the idea is quite simple to use. This is actually inspired and copied by the DRM dev unplug, enter, and exit functions that already exist for the DRM device itself. So it's nothing new, actually. So I've sent a first series here, which is currently under review, so you can have a look. The usage is very simple. Third chapter, some issues with the communication on the DSI case between the DSI host and the DSI device. So in our case, we have a DSI bus on the connector. So the host is on the baseboard, and the device is the bridge on the add-on. Most non-DSI bridge drivers in the probe function, they allocate the bridge, of course, and they call DRM bridge add to add the bridge to the list of known bridges in the system. That's a global list. And then they remove in the remove function. A DRM bridge remove in the remove function. This is not done in many DSI host drivers, not all, but many. Instead, most of the DSI host drivers call DRM bridge add when a device attaches, and they call remove when it detaches, which, first of all, looks a bit unnatural to me. Maybe it's perfectly fine, but it doesn't look as I would expect. But there are also practical implications. So one is, again, if the host bridge will not add itself, say you boot without an add-on connected, so the host bridge will not add itself, and so it will not be found by DRM, and DRM will not populate the video card. Oops, what is this? Okay. Yeah. So, so for the moment, I have a horrible workaround in the Hotplug bridge to handle this situation that I really would like to remove. And the other problem is that when you unplug and plug the add-on multiple times, the host, the bridge driver, which is on the baseboard, so it's not removable, will add and remove itself multiple times, which again looks a bit strange, and it also created some issues while implementing the second part of the debug.fs improvement I mentioned. So this is all under discussion. I've sent a series. There's a link in the slide. So this topic with the DRM bridge add is under discussion. I sent a patch to just move it to probe in one driver, the one I can physically test, and symmetrically move the DRM bridge remove to the remove function. This raised a lot of questions, which take a bit of time to be addressed, but discussion is in progress. And so that was chapter 3. Chapter 4 is, as I said, everything else. So finish the work. So there are some things that I definitely need to do. One which is still not totally clear is whether the Hotplug bridge should remain or be removed. So basically, if it is removed, that means DRM will be able to handle removal of the tail of the pipeline, and including some of the bridges on its own, with drivers doing what is needed. However, there could be some burden on the shoulders of the drivers to handle this, which might make the Hotplug bridge still useful. That will have to be seen depending on the outcome of the previous chapter. So it's still, let's say, future work to be addressed. Conclusion, there are two main parts of the work: the device tree description of the connector and the corresponding implementation. It is still blocked and slowly progressing at the specification discussion. We have a discussion with device tree maintainers later this afternoon, to try to sort out the core topics. And however, in the meantime, if you want to play with it, people who raised hand at the beginning, the implementation is well tested, in our case, and both by Ayush. So it is something that is working for the current device tree description. And on DRM, well, we have a plan, which is a good starting point, I guess. The plan is progressing, so chapter 1 is quite smoothly progressing at the moment, and the other 2 and 3 are slowly progressing out of the fog. So it looks like we are going to have work for some time. And yeah, so that's all. Thank you for your participation. I hope someone is still awake. Any questions? Any questions? Yeah, Laurent?
Thank you. Can you tell a few words about the component that determines which overlay to load? You mentioned there's an EEPROM, for instance, on the add-on board, or it could be something else. So you mentioned lots of APIs and components to enable all that. But can you explain a bit how you do the detection of the model?
Yeah, detection of the board is, so first of all, it is connector specific. In the connector we have, there are two I2C buses. On one of them, there is an EEPROM, along with potentially other devices. So the connector driver is the central part where this happens. The connector driver detects that there is an add-on through some GPIO or whatever, and then it loads a first overlay that describes enough to reach the EEPROM, which is, of course, at the same address on the same bus for every add-on. Then it reads the EEPROM content, and based on that, it knows which other overlay to load, and so it can load the rest of the overlay.
Okay, thank you.
Did you look at multiple connectors after each other, so stacking?
Yeah, stacking, recursive connectors, whatever you call them. Yeah, so an add-on which itself is a connector. I think they really exist in some products in the hacker-friendly developer boards. They do. So we don't have directly that use case, but in principle, using the same device tree structure, it should be possible because basically the idea is when you, let's see if I find some relevant picture somewhere. Yeah, so basically when you have, on the baseboard, you have an add-on connector, a connector node, and then you attach on top of that. And inside that, the part that you attach, you could have another connector, either with the same driver or with a different driver, and that in turn will do the same. Depending on device tree description, this could be problematic or not. So we are also trying to not break that use case in the description. There is a question there.
About this multi-connector stuff, there is this Turis Omnia router where you can stack connectors into one another. This is actual commercial product based on Marvel Armada.
Can you repeat the question? I didn't get it.
There is a Turis Omnia device. It's an actual commercial device where you can stack connectors into connectors into connectors. And it's on the market, and it runs Linux.
Yeah. So that's
but my question is different. My question is, how do you handle multi-function pins? Say you have a pin which can be either a GPIO or an I2C clock line, or say, for example, an SPI SCL.
Yeah, that leads to pinmux. So this is something that Ayush is handling in his proposals. So the idea with the exported symbols proposal, where is it? This one, yep. With the exported symbols proposal, that leads to exporting not only the connector node, but also multiple other nodes, which are the various, So not only exporting the connector node, but also exporting other nodes, each of the pinmux nodes that you want to use for the pin. So in the baseboard, you have pinmuxes for the various configurations of pins on the connector, I2C, GPIO, etc. And then you export all of these nodes on the connector. I see you are, wait a second. If I manage to exit this, here. So this is the right file. Yeah. So this is the patches sent by Ayush to support this. So in the baseboard, you have classic PMUX definitions, nothing special here. This is the label. And then in the connector definition, it is exporting multiple symbols, one per each of these PMUX configurations. So like the configuration where pin 1 and pin 2 are a GPIO controller needs this PMUX. The one where it is GPIOs needs those PMUX, and so on. And then in the overlay here, you mentioned those labels. So because you exported this symbol, this goes into the label exported by the baseboard. So again, it's all about the coupling. So this string here is in the middle. It represents the PMUX at the connector level. The baseboard tells how I implement it in my PMUX settings. And the add-on says how I'm using it to support this specific PWM whatever chip. This is, again, part of the discussion, so it's not set in stone. This is in our current proposal. I see you happy.
Hey, thanks for the great talk. So I have a use case which is pretty similar to yours, but also quite different. In my case, it's a reconfigurable FPGA region. Ooh. Yeah, you see where this is going, don't you? So basically, you have a region of the PL which has like firewall components around it, and you can decouple it and then just reprogram part of the PL. And this obviously leads to, there is support for this in Linux with the FPGA subsystem. You can insert an overlay and then tell in the device tree that I want to use this partial bit stream file and reconfigure this part. But if I remember correctly, I'm pretty sure it's not removable. And in my case, I need it to be removable so that you can swap in different regions, different PL programs. So my question is, do you think that this could fit into like somehow this connector abstraction?
I'm a bit rusty on FPGA support in Linux, but yeah.
Conceptually, maybe.
Conceptually, if you have a way to add and remove the region in the FPGA, which I'll happily leave it to you, then you'll need a connector driver. You may use a connector driver to describe the set of pins that are used by that FPGA region, exported pins on the FPGA pinout. And this connector driver needs to be able to know when you have inserted the FPGA region and when you unconfigure it. Other than that, it seems like it's the same mechanism. So you basically have removable hardware. It's in FPGA, but in the practice, it is removable hardware. Addable and removable hardware.
Okay, well, that's good news then. Thanks.
We can talk about that. All right. I think I'm out of time. No? No. Okay.
To the device discovery, you mentioned that I2C lines are defined and then EEPROM has to be there.
Can you repeat on the mic, please?
Back to the discovery question. You mentioned that an I2C line has to be defined and then an EEPROM has to be there. That sounds similar to what Raspberry Pi does with their heads. Would it also be feasible to define pin 1 and 2 as I2C lines and then, depending on the combination of I2C devices, say like this is add-on 2, this is add-on 1, this is add-on 2, this is add-on 3. So like I2C device A, B on the first one, C, D on the next, and D, E on the fourth one. Would that be doable?
I'm a bit lost.
Picture the I2C lines are defined, and then the add-ons have different combinations of I2C devices sitting on that bus. Not an EEPROM, but extension A has device A1, A2. Extension B has device A1, B2.
I assume mean the same connector, but parts of the connector is used by an add-on and part is used by another add-on?
No, I mean different I2C devices on the add-ons. And those make fingerprint for detecting the add-on itself.
I'm not sure I got totally the use case, but if it's an add-on or another add-on that have different devices, that's fine. It's supported by the whole mechanism.
So I have seen this in a lot of products where you just like probe the bus and check if a device is there. You don't have a dedicated EEPROM, but you just check.
I see. Yeah.
Okay, I have a panel, a touch controller, for example, at this address, then it's this panel. Oh, I have another touch controller, then it's that.
Okay, yeah. So you probe, you know that the extension have, you know the various extensions, so you probe and you see, okay, the touch is not found, so it's not this extension, and so on.
Fingerprinting.
It looks a bit fragile at first sight, poorly extensible. I mean,
You would need to know ahead of time which combinations you need to encounter.
yeah, of course, the connector driver can implement this or whatever policy makes sense. You could have, like, I've seen in the past products with like 3 pins, which can be either high or low, pulled up or pulled down. So you read those 3 with GPIOs on the baseboard, and you know which, you only have 8 possibilities, of course. Any technique can be implemented by the connector driver. So there is no one single way. Could be we are using I2C, which is by itself very flexible, but also a bit complex because we need to load a first overlay, then the model, and then load the second overlay. So it's a bit complex, but whatever algorithm, detection algorithm can be implemented in the driver.
I have a short tangential question. What's the status of actually loading overlays in Linux? So a few years ago, you needed patches to actually apply overlays at kernel runtime.
Loading overlays at runtime. So the status is the code inside the kernel to do that is there since a long time. It was, as far as I know, not exposed to user space in the mainline kernel until like 1 year or so ago. The previous talk by Hervé was about loading overlays for PCI. I don't know if you attended that. So that's, as far as I know, the first case where the possibility to load overlays was exposed to real use cases, except for test units, unit testing. This would be the second, if it happens. While the config.fs interface, which maybe you have in mind, which was proposed more than 10 years ago, I think, it is still maintained by Gert in his own branch. There he is. But it has been rejected, and as it is, as far as I know, it cannot be applied because it leads to various issues. One is fundamental. So an overlay can modify every node in the tree, which does not make sense in the use case for the connector, at least. Maybe it makes sense for other use cases, but not for a connector. And the other issue is that if the overlay is adding or modifying properties inside the node, which is in the base tree, this leads to memory leaks in the end. So I don't think I don't think there are work to change that. I'm not saying solve because I'm not sure it should be solved. Maybe it should just stay as it is.
Thank you.
But Christoph probably knows better than me. So, no, you don't? Okay. So let's not touch it.
Has somebody already thought about CSI, so camera interfaces, or on a connector?
No, we don't have a use case for a camera on the connector, but if you want to have a look at the work and report, try to add that, report. However, in that case, it's not quite device tree and overlays topic, but a video for Linux 2 topic. So as you see, half of the work is on our side on DRM. That would be a lot work, I guess, on video for Linux 2 as well.
Yeah, so about the CSI-2 connector use case?
What?
About the CSI-2 connector use case, which he was asking about. This will be very difficult because the Linux media subsystem is not really set up currently for doing anything hotplug. There's like a mechanism with async helpers where we wait for the whole tree to be populated, like the whole media controller tree. but then in this case, something would show up later, and then we cannot add it because there's really no way to add nodes later. And we also do not support hot unplugging stuff, which is also a big issue. So this would require a lot of work, the camera use case. It's not just the device tree overlay issue. It first needs a lot of core work in the
absolutely.
2 core.
I'm totally sure the video for Linux 2 part would be by far the most complex for that.
Yes.
Just like the DRM is for us. So I'm out of time. Thank you very much.